Blayac. I'm from France, coming from École de Saint-Étienne, and I'm working in the flexible electronic department. Our lab is near Marseille in France, and I represent the results of the work made by my PhD student, Ravichandran. So we'll talk about the contactless stretch sensor. So to start, just introduce some things about flexible, stretchable electronics that we already largely discussed during this conference. What we are doing in the department, we are working on this global system of flexible or stretchable substrates. So we are making some flexible micro batteries to have energy sources. We are designing some printed antennas, making some energy harvesting, and we work especially on thermoelectric and triboelectric energy harvesting, and also on sensors. So this presentation is not exactly on energy harvesting, but is on contactless stretch sensor, which has been derived from the triboelectric work that we did. Once all this is done, we integrate this in flexible or stretchable substrates. So to go to the sensor aspects, if we start from a given application like a smart skin, the interesting thing in stretchable materials is that you have a natural transduction of pressure of any mechanical solicitation into a deformation of the material. And that's interesting to exploit this stretchability, the softness of the material to fabricate sensors. So starting from this, we can then design some sensors that are derived from the principle of projected capacitance, the classical sensor that we have on our smartphones, for example, where you have two electrodes, you have some field line between the electrodes, and putting something in the field of the field lines will change the capacitance. To design the stretch and the touch sensor, we have designed structures that will be able to extract the different components of the mechanical solicitation, to extract a vector of deformation so as to mimic the characterization, the sensing function of the skin. So this is the first principle. The second principle is based on mechanical electrical transduction. We want to convert this mechanical variation into electrical signal. And one way to do this wirelessly is to put a charge insulator, which is an electrode, between two electrodes. In that way, we are able to directly translate any variation of position or variation of charge into directly a voltage without being without having to measure a capacitance. So the stretch sensor concept is the following. We just use stretchable materials as an insulator between two electrodes. There are two possibilities of integration. Where is the pointer? Here. Two possibilities. Either you can sandwich this electrode between the two electrodes, or having a planar structure like this. And then you have a certain charge in the insulator, and if you stretch the material, then you will modulate the charge density and obtain a voltage variation. That's what we are investigating for designing our sensor. So to fabricate this material, we start from PDMS films. We integrate some charges, some nanoparticles in it, and then we are able to put it in a stretching machine here and make the test of what we can do with it. Once it is done, sorry. video should start now. Once it is done, now we just have to charge it by corona effect. And we obtain some charge films that are ready to be used for test. We then put it in a stretching machine, and we obtain this kind of variation of position. And we study the electrical response of this film by just looking at the voltage that we have between the two electrodes, this with contactless configuration. So what we obtain, if we do this, we obtain this response in terms of electrical parameters, but this response is very strong and really straight. And this is not the actual response of the electret, but this is due to the variation of the position of the fixture here. So you have to shield the system so as to extract the exact response of the variation of the charge. And here you obtain a nice variation that will be an image of the stretching of the material. Then, if you want to evaluate the capacity of storage of our nanoparticles, we make a test just by using, for example, bare PDMS and then PDMS with 10% concentration of particles. And we can see that if we make some corona on the bare PDMS, we are making a charging but losing rapidly at the charge, and the signal is rather poor. But if we use then 10% concentration of charge, we have a rather high signal, and we can monitor wirelessly exactly the stretch of the signal. So the nanoparticles act as long-term charge storage sites, and we are now able to have a contactless sensor. So we studied the signal and the sensitivity of the function of nanoparticle concentration, and we obtained a maximum at 10% concentration with a good sensitivity of 250 millivolts per person strain, which is rather interesting. And the second thing important to see is that even without corona, we have some variation, and it's probably due to implicit triboelectric effects in the film that we designed. So in conclusion, we made an investigation on mechanical electrical transduction of stretchable materials. We developed some self-powered stretchable contactless stretch sensor with an interesting demonstration of sensitivity. The future work that we plan is to investigate dynamic behavior of the structure and extract resonant frequency. One important interesting feature of the system is that by just adjusting the stretching, you can also modulate the resonant frequency, so you can address some dynamic measurements. And then the remaining thing that we have to do is to integrate now the high impedance circuit, investigate on retention, and also address some specific applications with the device. To finish, I would just like to make an announcement. We have a project that is starting shortly. We will have several. It will be dedicated to the design of prototyping platform in 3D with different postdocs and different PhDs. So if people are interested, I propose them to contact me. So thank you all. If you have questions.
Thank you very much. Questions?
Hi. You showed the long-term stability of the surface potential over, I think, up to about 100 seconds. But can you comment on it any longer, sort of hours, days, weeks? The surface potential of the PDMS with the silver nanoparticles, how long does that last in terms of days, weeks, months?
here again, and we can move on. Next one, it's from, I guess, Wiley.